So now let us try to discuss the other method of designing pre-stressed concrete element, which is the Sealant Method or the center of pressure line method. So for the formulation or for the derivation of the formula for Sealant Method, actually we can start the discussion from the uh, formulation that we have conducted on the previous method that we have studied, which is the basic concept method. So we can actually use the information that we have found out on the derivation of the formula for the basic concept method, which are this. So for the case of Sealant method, usually this method is usually used on investigating or analyzing the stresses acting on the concrete element only at service load condition where the pre-stressing force is the effective pre-stressing force already, and the moment acting on the concrete element is the total moment coming from the moment due to the dead load or the self-weight itself, due to the superimposed dead load, and the live load. So usually, this method, Sealant method, is usually used for analyzing or investigating the concrete stresses acting on I mean, this method is usually used on investigating the stresses acting on the concrete element at service load condition. Although in my experience, actually, I have seen that you can also use this C-line method, this particular method, even on the other stages of pre-stressing, like for the case of initial pre-stressing at transfer and initial pre-stressing at transfer with self-weight. So in my experience, I think this C-line method can still be actually used on those uh, other two stages of pre-stressing. But uh, usually, C-line method is used for investigating concrete stresses at service load condition only. So for the formulation of the formula that we will use for the C-line method, actually we can start the discussion on this particular single force that we can see here, which is actually the uh, resultant of these stresses acting on the concrete, which are actually compressive stresses, and these stresses, which are actually tensile stresses. So remember, according to our previous discussion for the basic concept method, if we will try to get the resultant of this larger triangle here, larger triangular diagram, we know for a fact that the resultant of these flexural stresses we are seeing here from the larger triangle will point leftward, obviously. And for the case of the smaller triangle here, we know for a fact that the resultant of these flexural stresses here will point rightward. And if we will try to find the resultant of those two single forces, which are the resultant of this larger triangle and this smaller triangle, we can see that their resultant is actually a single force that points leftward. Why? Because obviously the direction of the resultant of the larger triangle will govern which is leftward. So obviously their resultant will be a single force pointing leftward, and we can just call that single force acting leftward as C, the total compressive stress we experience by the concrete elements. Actually, this is the uh, resultant compressive stress acting on the concrete element, obviously, because it points towards the concrete element itself, therefore providing a compressive strength, which is located at a distance, uh, at a certain distance from the center, located at a certain distance from the neutral axis or from the centroid of the cross-section of the concrete. So that single force, the total compressive stress, the total compressive force being experienced by the concrete cross-section is where we will start our derivation of the formula for computing stresses using Sealant method. So let us just focus on that single force, the total compressive force acting or being experienced by the concrete element. So again, take note guys, our color coding is all of the green forces or moments you will see here are the forces or moments or stresses acting on the concrete alone, while the purple one uh, is the force acting on the pre-stressing reinforcement. So for clarity, let us just move this single force total compressive force C near the concrete cross section for clarity of illustration. So let us just say that that single compressive force, the total compressive force acting on the concrete element, is at a distance A from the pre-stressing reinforcement or from the line of action of the pre-stressing force. So let us just say that the total compressive force acting on the concrete is at a distance A from the pre-stressing force acting on the pre-stressing reinforcement. And then let us just say again that the location of the total compressive force C is at a distance E prime from the neutral axis or from the centroid of the cross section. So again, let us just say the total compressive compressive force acting on the concrete section is at a distance A from the line of action of the pre-stress force acting on the pre-stressing reinforcement. And with respect to the centroid or to the neutral axis, let us just say that the total compressive force is at a distance E prime above the neutral axis or the centroid of the cross section. So what we actually have here is the free body diagram of the left segment of this particular concrete element here. So the forces acting on this left segment are the uniformly distributed load, the reaction, the total compressive force, and the pre-stressing force coming from the pre-stressing reinforcement. Now we know that this original structure here, this original figure here, is in equilibrium. We know that for a fact. And since the whole structure is in equilibrium, since the whole structure is in equilibrium, therefore its segments must also be in equilibrium. So meaning all of the forces that you see here must balance each other with respect to the total force and the total moments or moment acting on this left segment. So if you can if you can recall from statics, if we say that our body or our element here is in equilibrium, therefore if you will sum up all of the horizontal forces acting on it, their sum must be equal to zero, meaning there is no tendency to move along the horizontal direction. So you can see here the only horizontal forces acting here on this left segment are actually the total compressive stress and the pre-stressing force acting on the pre-stressing reinforcement. So if we will just say that rightward 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 forces are positive, so that is our sign convention. Let us just say that all rightward forces are positive. So summing all of the horizontal forces, we can say that P minus P is pointing rightward, so it has a positive sign, while the total compressive force is acting leftward, so it has a negative sign, but I just move it on the right side of the equation to have an equation which shows that the total compressive force acting on the concrete is just equal to the magnitude of the pre-stressing force acting on the pre-stressing reinforcement. So we have found out that the total compressive force is just equal to the pre-stressing force acting on the pre-stressing reinforcement according to this equation that we solved using the uh, one of the equations of equilibrium from statics. So another thing from statics that we have to satisfy is that all of the forces here, I mean the moments acting on this particular left segment must also be balanced. So therefore, if we sum up all of the moments, all of the forces that has moments acting on this left segment, the summation of their moments must be equal to 0 in order to say that this left segment is in equilibrium. So if the summation of moments is equal to 0, therefore it means that there is no tendency to rotate at this particular segment of the concrete beam we are considering here. So if we will sum up the moments produced by this uniformly distributed load W and the reaction, the upward reaction here, if we will try to get the moment of the uniformly distributed load and the single force reaction here with respect to this cross section, we can say that uh, their resultant moment uh, is a moment M which has a direction of clockwise. Clockwise direction because obviously the moment produced by the reaction will obviously be larger than the moment produced by the uniformly distributed load here, therefore producing a clockwise moment because the moment produced by the reaction is clockwise. So its direction will govern. So it will have a clockwise moment M. That's just called the summation of their moment with respect to this cross section as moment M, which has a clockwise direction. And since we said that clockwise moments are positive, so the moment M, the sum of the moments of the uniformly distributed load in the reaction will have a positive uh, value here on our equation, since obviously it has a clockwise moment. And then, if you can observe here, since we have known that P is equal to C, the pre-stressing force is just equal to the total compressive force here. Therefore, we can see here that there is, I mean, they produce what we call a couple. So let us just review what is the meaning of a couple. So a couple comprise of uh, two parallel forces with equal magnitudes but opposite in direction, just like in the case here. Since the total compressive force and the pre-stressing force have equal magnitude according to this equation, and obviously they are parallel and opposite in direction. Therefore, they produce a what we call a couple. And a couple has a zero resultant, but it has a resultant moment, which is actually called couple moment, which usually has a magnitude equal to the product of the magnitude of either of the two forces and the perpendicular distance between them, which is in this case the distance A. So therefore, the moment that is being produced by the pre-stressing force and the total compressive force here is a couple moment with a magnitude of C times A or P times A. So either of the two. So let us just use uh, PA or CA. So the direction of their moment, the couple moment, is obviously counterclockwise. So it must have a negative sign. So I just again already move the negative PA or negative CA from the left side of the equation to the right side of the equation. So I hope everyone can follow what happened here. So I just move the negative PA or negative CA from the left side to the right side of the equation to have this expression here. So from this expression, we can see that A, the distance from the total compressive force and the pre-stressing force, is actually equal to the ratio of the bending moment acting on this cross section due to the external loads, the uniformly distributed load and the reaction here, divided by the pre-stressing force acting on the pre-stressing reinforcement. So that is how you can get the distance between the pre-stressing force and the total compressive force. So, if you will refer here as well on this figure, we can see that E prime is actually equal to A minus the eccentricity E, or in equation form, E prime is equal to A minus E. And since A is equal to M over P, therefore we can substitute the value of M over P in place of A here, thereby producing this equation. E prime is equal to M over P minus E. So this is how you can get the distance of the, or I mean the distance of the total compressive force with respect to the neutral axis or the centroid. So you can use this formula. The bending moment due to the external loads, Wn reaction, divided by the magnitude of the pre-stressing force minus the eccentricity of the pre-stressing reinforcement. So that is how you can get the magnitude of E prime. So actually, the magnitude of E prime, or in other words, the location of the total compressive force C acting on the concrete element, will actually vary starting from E prime is equal to E, wherein, as you have seen on the derivation of the basic concept method, we have seen that if the only forces acting on the left segment here, on the concrete element that we have here, is the pre-stressing force alone, we have seen that the total compressive force acting on the concrete uh, will be located on the same location of the pre-stressing reinforcement, which is here. So you can just imagine that this total compressive force is acting here. Originally, if the only forces acting on the left segment is the pre-stressing force alone. And then after the concrete element up bend upward, thereby producing camber, and thereby forces itself to support its own weight, the magnitude of the location of the total compressive force C will slowly move upward as you apply an uniformly distributed load to the concrete element itself. So again, originally, if there are no external loads here applied to the concrete element, if the force acting on the concrete element is the pre-stressing force alone without the external loads, we can say that we have seen from the previous discussion, from the basic concept method, that the total compressive force is acting collinear to the line of action of the pre-stressing force here. And then as you add a uniformly distributed load there, coming from the self-weight of the concrete element itself, the total compressive force tends to move upward slowly, thereby producing a negative value of E prime, since the distance from the neutral axis or centroid to the location of the total compressive force is below the neutral axis. Therefore, its sign must be negative. It must have a negative value of E prime, since it is located below the neutral axis or the centroid. And then it will slowly move upward up to the centroid, location of the centroid, wherein the value of E prime is equal to 0. And then as the concrete element supports these additional loads coming from the superimposed dead load and live loads, the location of the total compressive force will again slowly move upward to a location, or up to a distance equal to A prime. So as you add the superimposed dead load and live load to the concrete element, again, the location of the total compressive force will slowly move upward up to a distance E prime from the neutral axis or from the centroid. So again, if you want to find the magnitude of E prime, you can just use this formula that we have formulated here. And again, if the location of the total compressive force is acting above the centroid or the neutral axis, the sign of E prime will obviously be positive. Otherwise, if it is acting below the centroid or the neutral axis, it will have obviously a negative value, the A prime. So this total compressive force here, the total compressive force C, can actually be moved from this location to the location of the centroid, just like what we did on the basic concept method. So we can actually transfer that to this particular location, to the location of the centroid. And according to statics, if we want to transfer a force to a different location, there must be a moment that must be produced or introduced, which is in this case, which the moment that will be introduced will be the product of the compressive force C and the perpendicular distance between its line of action and the location where we want it to be transferred, which is in this case with respect to the neutral axis or the centroid. And obviously, the moment that is being produced by the compressive force C to the neutral axis or the centroid is just equal to the product of C and the perpendicular distance E prime. So the moment that it produces is actually a counterclockwise moment, which has a magnitude of CE prime. So that is how we can transfer this single force C here to the location of the centroid. So since we already transferred it, we can already remove that single force acting at a distance E prime from the centroid. And again, just like in the basic concept method, since we have here an axial force and a bending moment, which is actually the moment produced by the total compressive force due to the eccentricity of the total compressive force, this force and this moment will actually produce an axial force, an axial stress and a flexural stress with respect to the concrete element. So the single force C, the axial force C acting on the centroid or the neutral axis will actually produce what we call axial stresses, which is uh, assumed to be uniformly distributed all throughout the concrete element. And its value will obviously equal to the magnitude of C divided by the total cross-sectional area of the concrete. Or since uh, C is equal to P, we can replace C by P, since according to this equation, C is equal to P. So that is the stress produced from the application of the total compressive force acting on the centroid. And in the case of the bending moment CE prime that is produced by the eccentricity of the total compressive force a while ago, it will produce flexural stresses, which will look something like this, which actually have a total. If you will try to investigate this diagram, the flexural stresses resulting from the bending moment CE prime. So it is composed of uh, several equal forces, equal in terms of with respect to the centroid or neutral axis. So we have here equal forces with opposite directions, which again produces what we call couple and produces as well a what we call couple moment. So if you can imagine, the resultant of this triangle points leftward, while for this triangle, it points rightward. And obviously, they have a same magnitude of resultant but opposite in direction, thereby producing what we call a couple moment equal to this bending moment here. Because obviously, these flexural stresses just came from the bending moment CE prime. With a extreme fiber stress here acting here at the top of the concrete element equal to MC over I, wherein we will just replace M by the bending moment CE prime. And again, since C is just equal to P, we can also replace C by P, thereby producing this formula acting on the extreme top fiber of the concrete. And again, take note of the sign negative because obviously this uh, stresses here points towards the toward the concrete element itself, thereby producing compressive stresses. So we indicated a negative sign to indicate that the stresses are actually compressive stresses. And in the same manner, we can compute for the extreme fiber stress at the bottom of the concrete element equal to again MC over I, and just replace M by CE prime. And since C is just equal to P, we can also replace C by P. And again, since this forces point away from the concrete element, thereby producing tensile stresses, we have to indicate that the magnitude of the extreme fiber stress is a tensile stress with indicating a positive sign to indicate that it is a tensile stress. So if we will try to add these stresses being produced by the total compressive force acting a while ago at, at an eccentricity E prime from the centroid or neutral axis, if we will try to add or get the total stress coming from that total compressive force acting here a while ago, the diagram will look something like this, with a extreme fiber stress, total stress at the top equal to this, which is just the sum of the actual stress, negative P over AC, and the stress here, which is negative PA prime CC over IC. And in the same manner, you can get the total stress acting at the bottom, which is just again the sum of this, negative P over AC, and this, which is PE prime CT over IC. So these are the total stresses acting on the concrete element itself. Actually, these formulas that you are seeing here are the formulas that we can use for finding the total stresses acting on the concrete element using the Sealant method. So these are the formula that you have to remember if you want to find the concrete stresses acting here using Sealant method or center of pressure line method. So if you can notice, these formulas actually are just the same on the formulas that we have derived from the previous discussion about the basic concept method. If you can notice, they are just equal. If you can remember, these are the formulas we have gathered from the basic concept method. And again, actually, these formulas are just equal to these formulas that we have derived here on the C-line method. So how is that? How was how was those formulas became equal? How did we say that this formula and this formula and this formula are equal? How can we say that they are equal? So if you will put your attention here on this equation, A prime is equal to M over P minus E. If we will try to rearrange this, if we will try to multiply the whole equation by magnitude P so that we can remove the denominator, we will have this expression. PE prime, multiply this by P, PE prime is equal to M because the P will be cancelled, minus PE. So if you will notice, we have seen that PE prime, the PE prime here is just equal to M minus PE. Meaning if we will just factor out C over I here, thereby we can see that uh, the M minus PE expression, if we will try to factor out C over I here, is just made to be equal to PE prime here. So in other words, this formula is actually the same as this formula, but just seen on a different perspective. So technically, they are just equal, but they are just seen on a different perspective. So in this case, we just uh, we just seen the difference between the bending moment and the uh, bending moment coming from the eccentricity of the pre-stressing force as equal to this expression, PE prime. So again, if we will try to factor out C over I here and C over I here, we can get an expression equal to M minus PE if we will also factor out the negative sign. So again, that M minus PE was just replaced by PE prime on this expression. So again, like what I want to point out here, this formula we got from the Sealant method is just actually equal to the formula that we got from the basic concept method. So technically, they are just the same, but just seen on a different perspective. We are just looking this formula in terms of the bending moment and the moment produced by the pre-stressing reinforcement. And we are just looking at this formula with respect to the pre-stressing force and the distance of the total compressive force with respect to the neutral axis. So technically, they are just the same. So if you will try to get again the resultant of this stresses acting on the concrete element, again you can see that the total uh, the total of these stresses you see here is actually a single force C, which is the total compressive force that we are talking about here. This is just actually the same on the total compressive force we are talking about here a while ago. So if you will try to get the sum of these flexural stresses you are seeing here, you will get the same magnitude with the same location of total compressive force. So at a certain distance from the centroid. So they are just the same. So that is how the formulas for the C-line method or center of pressure line method are derived. So again, these are the formulas for center C-line method or center of pressure line method. So it's called C-line method or center of pressure line method because we are just focusing on this C line. It is actually what we call the C line. So the compressive force, the total compressive force acting on the concrete element.